A recent breakthrough has been made in the field of brain-computer interfaces, or BCI, that is going to enable researchers and developers to greatly increase the fidelity of systems that patients are receiving. To understand how this system works, let's take just a quick look at how our brain works. Your brain wants you to pick up a glass of water, so it's going to send a motor signal down to your arm to pick it up and move your muscles to do so. And then your arm is going to tell your brain what position it's in and how that motor plan was executed and whether or not it was successful. And so your brain is going to compare these two states. It's going to compare them to see if it likes the result. And if it is successful, well, then good, and your brain continues to have that high fidelity control over your muscles. And if it didn't work, then it's going to slowly adjust it so that what happens the next time it does it will look like what it wants it to look like. And so this is the simple concept behind a closed feedback system, wherein you get an input to the system and you get not only an output but also feedback that will influence further outputs. Your brain has entire systems or entire areas related to this process. Both the cerebellum and the sensory cortex perform this task, and it's incredibly important in performing fine motor functions. And so the issue with a lot of modern BCIs is that they don't have a way to send information up into the brain to give the brain something to go off of. So we can get information out via EEGs or ECOGs, but getting it in is exponentially more difficult. And what these researchers, Tall and others, have demonstrated is a way to optogenetically stimulate neurons within the cortex to get them to feel something. This device is 4 shanks with 124 OLEDs. And what they do is they stick this inside the brain like this. This is a mouse. This is a mouse brain. Only been done on mice, but it's an organism. And by turning on either the orange or the blue LEDs, they are able to stimulate or silence or relax the cortical neurons that are in the vicinity of the light. How they do this is by optogenetically transforming these neurons to express either CHR-MINE or channel rhodopsin 2. So these orange LEDs activate channel rhodopsin MINE, and the blue ones activate channel rhodopsin 2. This way, they're able to get essentially 2,048 individual different signals that they can send into the brain, and they use this to essentially show that this system has such good specificity for the neurons that it wants to activate that you can get single neurons. As in, when this OLED is activated, you get this signal. You get this signal from the neuron that's next to it. And when this is activated, you get this signal from the neuron that's next to it, and you get this signal from this neuron. Now, if we want to think about this a little graphically, what this is essentially just the shank going deep into the brain. So up here is the top, and here are the lower layers of the cortex. And so as we're going down, we are going to layers 5, 6. And so while these are layers 2 and 3, like cortical interneurons, this at the bottom, neuron 3 that they're activating, is a pyramidal neuron, an excitatory neuron, one of the neurons that tells your muscle to, hey, move your bicep. And so they're able to target not just individual neurons, but the layers within the cortex itself. And so here's just a better view of that. As you can see, when OLED group 1 is turned on, neuron 1 is firing, and neuron 2 is not firing, and neither is 3. There's no change in their activity. But when group 2 turns on, well, neuron 2 lights up immediately, but neuron 1, neuron 3 don't. And so this is the crux of the excitement, because by putting this relatively stable implant into a mouse's brain, we can address these neurons, like they're a transistor, and tell them, turn on, activate. And by doing this, it may end up being possible to give feedback to the brain for any number of processes. Now, going beyond this, they're not only able to excite individual neurons, but something called the local field potential. And this is just a measure of all the neurons that are connected to the other neurons that are next to it. And slowly, as you excite more and more and more, you'll get a big field of neurons. And so you're not just recording from this one, you're recording from all of them. And this becomes quite a good proxy for circuit level activation. So when they when they activate it in pulses like this, they get very, very high activation of the local field potential, compared to what is the baseline without this optogenetic stimulation, without these LEDs just flashing in the brain, which I want to remind you of, because that's what makes this really cool. It's just LEDs flashing in the brain, and through those channel rhodopsins is telling the neurons to, hey, turn on, or hey, turn off. Now, this local field potential activation is also specific to the layer of the brain. And so here, when this OLED group turns on, you can see the difference in waves as we go down into the tissue, showing that, well, as they quantify later, it's penetrating 1.5 millimeters of tissue. The light will penetrate 1.5 millimeters of tissue and effectively activate most of those neurons. And of course, if you turn up the power, you get more activation. So then, what can we do with this? Well, this is really new. This is, remember, 2023. So no one's put this in a monkey or let alone a human yet, and done behavioral things. But someone has done a Drosophila larvae. Now, this isn't the exact same setup because these Drosophila larvae aren't being shanked with these OLEDs. They're simply sitting on a pad that will turn on. However, their neurons are still expressing a channel rhodopsin. They're not expressing two different kinds, but they are expressing either crimson or GTACR2. Crimson tells the neurons to turn on and activate, and GTACR2 tells them to calm down. And so what happens when they place this larvae on the OLED and turn it on is their behavior changes. You see a behavioral change. When they're expressing crimson, then their neurons are activating in response to the OLED, and 95% of the time you get whole body contraction. They're spasming, they're freaking out, they're moving all about. And when they're expressing GTACR2, they're chilling out. They're more often than anything else just slowing down and just kind of undulating. And then the other part of the time they're relaxing. So they show that the excitatory circuit gets turned on with a great degree of reliability, and I mean 60% is pretty good. 60-ish% is pretty good, but not quite 99 for the relaxatory circuit, or the inhibitory neurons. And so here is just an awesome image of what this contraction looks like. So the OLED is within these blue borders, and when it turns on, the larvae moves about. It shrinks and squirms, and this is a really positive indicator for this technology being of some use in organismal BCI, higher order life